Imagine standing on a platform, ready to be dematerialized, your atoms scanned and then reassembled light years away. It's a staple of science fiction, most famously the transporter from Star Trek. Generations have watched Captain Kirk and his crew beam down to strange new worlds, seemingly defying the laws of physics with a push of a button. But how much of this is actually rooted in science and how much is pure fantasy? Is it even remotely possible to turn a person into a stream of energy and then put them back together again? For decades, teleportation has been a tantalizing promise, fueled by countless films, books, and television shows. From the instantaneous travel in the movie Jumper to the more unsettling implications explored in The Fly, the idea of moving matter across space has captured our imaginations. Writers like Isaac Asimov and Arthur Clarke explored the concept in their stories, weaving tales of both wonder and potential danger. These fictional depictions have shaped our understanding or perhaps misunderstanding of what teleportation could be. They've planted a seed of possibility, whispering that one day, perhaps, we too could bypass the limitations of space and time. But let's peel back the layers of fiction and confront the cold, hard facts of science. The teleportation envisioned in Star Trek, while visually impressive, relies on technologies that remain firmly in the realm of science fiction. The show's transporters work by converting matter into energy, transmitting that energy to a distant location, and then converting it back into matter. The question is, can this even be done? The reality is far more nuanced and infinitely more complex. The scientific concept of quantum teleportation is not about physically moving matter, but rather about transferring information. Imagine two locked boxes. Quantum teleportation would allow you to transfer the contents from one box to another without ever opening them, destroying the contents in the original box in the process. It's a mind-bending concept, one that challenges our fundamental understanding of space, time, and reality itself. It also differs greatly from what is presented in science fiction. So how does quantum teleportation actually work? And more importantly, does it hold the key to one day transporting a living, breathing human being? Could we ever step onto a platform and be instantaneously reconstructed on the other side of the galaxy? That's what we want to find out. Is human teleportation just a dream, or is there even a flicker of possibility within the quantum realm? It is a question that forces us to confront the very nature of reality and to ask ourselves a fundamental question. What does it truly mean to be human? So human teleportation remains a distant dream, at least for now. But to truly understand why, we need to journey into a realm far stranger than even the most imaginative science fiction. A place where the rules of reality bend and break, where particles can be in two places at once, and where observation itself changes everything. Welcome to the quantum realm. It's a universe operating at scales almost incomprehensibly small, the domain of atoms and the subatomic particles that comprise them. Here, the familiar laws of classical physics, the ones that govern our everyday experiences, simply don't apply. Imagine a world where a coin spinning in the air doesn't land on heads or tails, but exists in a blurry, undefined state of both at the same time. That's superposition, a cornerstone of quantum mechanics. A particle can exist in multiple states simultaneously until the moment we try to measure it. It's like the particle is making up its mind only when it knows we are watching. Think about it this way. You're walking in a forest. In the classical world, you're either walking north or south. In the quantum world, you are walking in both directions at the same time until you stop to check your compass. Only then does the quantum fog clear and you commit to a single direction. This bizarre behavior isn't just some theoretical oddity. It's a fundamental property of matter at the quantum level. But it gets even weirder. Consider the act of observation itself. In our macroscopic world, we can observe something without fundamentally altering it. We can look at a car without changing its speed or direction, but in the quantum world, observation is an active process. The very act of measuring a quantum particle forces it to choose a state. collapsing the superposition. It's like trying to peek at someone playing hide and seek. The moment you look, you've given away your position and changed the game. These seemingly counterintuitive concepts are built upon the foundation of fundamental particles and forces. Everything we see, touch, and experience is ultimately made up of these tiny building blocks, quarks and leptons, held together by forces mediated by particles like photons and gluons. These forces, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, govern interactions at the smallest scales, dictating how these particles behave and interact. Understanding these interactions is crucial because teleporting a human wouldn't just involve moving atoms, it would require perfectly replicating their quantum states and interactions. But how do you even begin to wrap your head around such a complex and strange world? Scientists have spent decades grappling with these questions, developing mathematical models and conducting experiments that push the boundaries of our understanding. And while many mysteries still remain, one thing is clear. The quantum realm is a world of limitless possibilities and profound implications, a world we must understand if we are to even begin to contemplate the possibility of teleporting something as complex as a human being. Because within this quantum universe lies the key to perhaps the strangest phenomenon of all, something Einstein famously called spooky action at a distance, a phenomenon known as quantum entanglement. Imagine two coins, flipped at the same time, but instead of landing randomly, they are linked. If one lands on heads, the other instantly lands on tails, no matter how far apart they are. Sound like science fiction? It's not. It's quantum entanglement, a real and baffling phenomenon that Einstein famously dubbed spooky action at a distance. But is it truly spooky, or is it a key to unlocking the secrets of the universe and perhaps even teleportation? Quantum entanglement occurs when two or more particles become linked together in such a way that they share the same fate. This interconnectedness is so profound that measuring the state of one particle instantaneously influences the state of the other, regardless of the distance separating them. Imagine Alice has one of these entangled particles and Bob has the other. They could be in different labs, different countries, or even on different planets. When Alice measures her particle and finds it has a specific spin, Bob's particle will instantaneously have the opposite spin, even though no physical connection exists between them. This instantaneous connection is what baffled Einstein. He couldn't reconcile it with his theory of relativity, which states that nothing can travel faster than the speed of light. How could these particles communicate instantaneously across vast distances? Einstein believed that there must be some hidden variables at play, some underlying mechanism that explained the correlation without violating the laws of physics. He argued that quantum mechanics was incomplete, that there was more to the story than what was being revealed. But numerous experiments have since confirmed the reality of quantum entanglement. One of the most famous experiments, conducted by Alain Aspect and his team in the 1980s, demonstrated that entangled particles remain connected even when separated by considerable distances. This experiment provided strong evidence against Einstein's hidden variables theory and solidified entanglement as a fundamental property of the quantum world. The implications of entanglement are staggering. It suggests that there is a deeper level of reality, a realm where the familiar notions of space and time break down. It's as if these particles are not individual entities, but rather different aspects of a single, unified whole. It is a concept that challenges our classical intuition and forces us to rethink our understanding of the universe. But how does entanglement actually work? Well, it begins at the creation of the entangled pair. These particles can be created in a number of ways, such as by splitting a single photon into two entangled photons, or by allowing two atoms to interact in a specific way. The key is that the particles are created in a correlated state, meaning that their properties are intertwined from the very beginning. Think of it like buying a pair of gloves. You don't know which glove is left and which is right until you open the package, but once you see one, you instantly know the other. However, with entangled particles, the connection is far more mysterious and instantaneous. This brings us back to the question of teleportation. How can entanglement be harnessed to transport information or even matter? The answer, as we will see, lies in a clever protocol that combines entanglement with classical communication. It involves Alice, Bob, and a carefully orchestrated dance of quantum states, bringing us closer to understanding the true potential and the limitations of quantum teleportation. Just how close are we to using this spooky action to beam something across the cosmos, and what challenges still stand in our way? Quantum entanglement, that spooky action at a distance, is more than just a theoretical curiosity. It's the engine that drives the strange and remarkable process we call quantum teleportation. But forget those images of people dissolving into particles and reappearing somewhere else. The reality, at least for now, is far more subtle, a delicate dance of information and quantum states. So, how does this cosmic ballet actually work? The quantum teleportation protocol, as it's known, involves three key players: Alice, Bob, and an entangled pair of particles. Alice, the sender, wants to teleport the quantum state of a third particle, let's call it particle C, to Bob, the receiver, who might be miles or even light years away. The crucial ingredient here is the entangled pair, particles A and B. Alice takes particle A and Bob takes particle B. These particles are linked in such a way that their fates are intertwined, regardless of the distance separating them. Now, Alice holds particle C, the one whose quantum state she wants to teleport, and particle A, her half of the entangled pair. The next step is where things get truly bizarre. Alice doesn't directly measure the state of particle C. Instead, she performs a joint measurement on particles A and C. This measurement is designed to entangle particles A and C together. The result of this joint measurement gives Alice 2 bits of classical information. Think of it like flipping 2 coins. You have 4 possible outcomes: heads heads, heads tails, tails heads, or tails tails. These 2 bits of classical information are absolutely crucial. This is because they tell Alice something about the relationship between particles A and C, but more importantly, they are the key to unlocking the quantum state on Bob's side. Here's where the classical communication channel comes into play. Alice must communicate these 2 bits of information to Bob using a conventional method. Think email, a phone call, or even a carrier pigeon if you're feeling retro. It's important to note that this part of the process is limited by the speed of light. There's no faster-than-light communication happening here, despite what you might think. Einstein can rest easy. Once Bob receives these 2 bits of classical information from Alice, he can perform a specific operation on his particle B, the other half of the entangled pair. The operation he performs depends entirely on the information he received from Alice. Depending on whether Alice measured heads heads, heads tails, tails heads, or tails tails, Bob will apply a different transformation to particle B. And here's the magic. After Bob performs the correct operation, his particle B instantly takes on the exact quantum state of particle C, the original particle that Alice wanted to teleport. In effect, the quantum state has been teleported from Alice to Bob, but there's a catch, and it's a big one. The very act of measuring particles A and C on Alice's side destroys the original quantum state of particle C. It's like taking a photograph. The moment you capture the image, the original scene is altered. The same holds true for quantum teleportation. The original quantum state no longer exists at Alice's location. It has been perfectly transferred to Bob, but it's gone forever from its original location. So it's not about moving the particle itself. It's about transferring the information, the delicate quantum state, from one place to another. The original is destroyed in the process, making way for a perfect copy to emerge elsewhere. Now, before you start planning your next vacation via quantum teleportation,
It's critical to understand what this actually means. Scientists aren't teleporting matter. They are transferring quantum states. Think of it like sending a blueprint rather than the actual object. The blueprint contains all the information needed to rebuild the object, but the original object is still required to create the copy.
The implications of this are profound. Quantum teleportation could revolutionize quantum computing, allowing for the creation of powerful quantum networks. It could also lead to unbreakable encryption, securing our communications from eavesdropping. But teleporting a human being? That's a challenge of an entirely different magnitude, one that pushes the boundaries of our understanding of physics and perhaps even reality itself. Just how far are we from scaling up this incredibly precise transfer of quantum states from atoms to human beings? The answer, as we'll see, involves facing some of the most fundamental laws of the universe, and it may rewrite everything we thought we knew about copying. Imagine holding a priceless work of art, a painting by Van Gogh, a sculpture by Michelangelo. You want to share its beauty, its intricate details, with the world. But what if the only way to do so was to destroy the original in the process of creating a copy? That's the unsettling reality at the heart of a fundamental law of quantum mechanics, a law that throws a major wrench into our dreams of human teleportation. It's called the no-cloning theorem, and it states something quite profound. It is fundamentally impossible to create an identical, independent copy of an arbitrary, unknown quantum state. But what does this mean, and why is it such a headache for anyone hoping to beam themselves across the galaxy? The no-cloning theorem isn't just some abstract mathematical concept cooked up in a physics lab. It is a bedrock principle woven into the very fabric of quantum mechanics. To understand why it exists, we need to delve a little deeper into the mathematics that governs the quantum world. In essence, the theorem arises from the linearity of quantum mechanics. Without getting bogged down in equations, linearity implies that the rules that govern how quantum states evolve over time are consistent and predictable. They don't allow for the kind of non-linear transformation that would be required to copy an unknown quantum state. Think of it like this. Imagine you have a simple machine that takes an input and produces an output. If the machine is linear, then doubling the input will always double the output. The no-cloning theorem says that you can't build a quantum machine that will perfectly copy any input you give it. No matter how clever you are, there will always be some quantum states that the machine simply cannot duplicate. But what are the implications? Why can't we just build a perfect quantum Xerox machine? The problem lies in the act of measurement. As we've discussed, measuring a quantum state inevitably disturbs it. In other words, to copy a quantum state, you would first need to measure it to determine its precise properties. But that very act of measurement changes the state, destroying the original information. It's like trying to catch a butterfly with a net. The act of catching it inevitably damages its wings. The no-cloning theorem has profound implications for quantum information theory. It is, in a way, a double-edged sword. On one hand, it limits our ability to manipulate quantum information. We can't simply copy quantum data like we can with classical data. But on the other hand, this limitation provides a powerful foundation for secure quantum communication, because any attempt to eavesdrop on a quantum communication channel to copy the quantum information being transmitted would inevitably leave a trace, alerting the sender and receiver to the presence of an interloper. It's like having an unpickable lock on your most sensitive data. So where does this leave our dreams of human teleportation? Well, it presents a pretty significant obstacle. Remember, teleporting a person wouldn't just involve moving atoms. It would require perfectly replicating their quantum state, every single property of every single particle that makes up their being. But the no-cloning theorem tells us that this is fundamentally impossible. We can't create an identical copy of an unknown quantum state. So it seems we can't simply duplicate a person via quantum means. Does this mean that human teleportation is definitively ruled out? Not necessarily. The no-cloning theorem applies to creating an independent copy. It doesn't necessarily forbid transferring a quantum state, as we saw with quantum teleportation, but remember that process involves destroying the original, so if we were to teleport a person, the original would have to be destroyed in the process. The question then becomes, is the teleported you still you, or just a perfect copy with all of your memories? A philosophical minefield, to be sure. Perhaps you are wondering about the mathematical reasons behind this perplexing law. The answer is rooted in the mathematics of quantum mechanics. The equations that govern quantum systems are linear, meaning that they preserve the structure of quantum states. Copying, on the other hand, is a non-linear operation. So is there any way to circumvent it? The universe, it seems, has set a very strict rule. A rule that for now seems to keep human teleportation firmly in the realm of science fiction. But in the ever-evolving landscape of quantum physics, surprises are always possible. And the implications of this seemingly insurmountable theorem are only beginning to be explored. The questions about what we can copy, what we cannot, and what this might mean for the future of the human race remain open. But is all of this just theory? Beautiful mathematics and mind-bending thought experiments that will forever remain confined to the chalkboards of physicists? The good news is, absolutely not. While human teleportation remains a distant prospect, scientists around the world are actively pushing the boundaries of quantum teleportation, achieving breakthroughs that were once considered the stuff of science fiction. Imagine a laboratory, sterile and humming with the quiet energy of cutting-edge technology. Here, researchers are meticulously manipulating the tiniest building blocks of reality, not to construct skyscrapers or design new materials, but to teleport information. The targets of their experiments are not people or even molecules, but photons, those fundamental particles of light that carry energy and information across the cosmos. For years, teleporting the quantum states of photons was the holy grail of quantum teleportation research, a proof of concept that would validate the theoretical framework and pave the way for more complex experiments. And then, it happened. In 1997, a team led by Austrian physicist Anton Zeilinger at the University of Innsbruck achieved a monumental breakthrough. They successfully teleported the quantum state of a photon to another photon, marking the first experimental verification of quantum teleportation. The experiment, while incredibly complex, involved creating entangled pairs of photons and then using them to transfer the polarization state of a third photon. It was a landmark moment, a confirmation that quantum teleportation was not just a theoretical possibility, but a real phenomenon that could be harnessed in the laboratory. This initial success ignited a global race to push the boundaries of quantum teleportation even further. Scientists began exploring new ways to improve the fidelity and distance of teleportation, experimenting with different types of particles and developing more sophisticated techniques for entanglement and measurement. In the years that followed, researchers successfully teleported the quantum states of atoms, the fundamental building blocks of matter. Atoms are far more complex than photons, possessing a multitude of internal states and energy levels. Teleporting their quantum states required even greater precision and control, a testament to the relentless ingenuity of the scientific community. One particularly groundbreaking experiment conducted at the National Institute of Standards and Technology in Boulder, Colorado, involved teleporting the quantum state of a beryllium ion, a charged atom, over a distance of 1 meter. While 1 meter might not sound like much, it was a significant achievement, demonstrating that quantum teleportation could be achieved with high fidelity and over a measurable distance. Moreover, this experiment also showcased the potential for using ions as qubits, the fundamental units of quantum information, paving the way for the development of quantum computers. But the quest for longer distances continued. In 2015, researchers at Delft University of Technology in the Netherlands achieved a remarkable feat. They successfully teleported the quantum states of electrons over a distance of 1.3 kilometers. This experiment was particularly significant because it used a real-world fiber optic cable to transmit the classical information required for teleportation. It was a crucial step toward building quantum networks, secure communication channels that could transmit information with absolute confidentiality. And the achievements keep coming. Scientists have even managed to teleport the quantum properties of entire groups of atoms. This is a huge step toward practical quantum computing because quantum computers need to manipulate and transfer information between many qubits to solve problems. Think of it as going from sending a single letter to sending an entire book. The challenges are immense, requiring extraordinary control over the quantum environment. These successes aren't just about bragging rights for scientists. They represent monumental leaps in our control over the quantum world. Each tiny teleportation is like a single, perfectly placed brick in a road that might, someday, lead to technologies we can only dream of today. They show that this weird quantum world, once thought to be forever beyond our grasp, can be manipulated, controlled, and even used to transfer information in ways that defy our classical intuition. However, let's be clear. These are still incredibly small steps. We are talking about teleporting the quantum states of single particles or small groups of atoms, not complex organisms like human beings. Scaling up quantum teleportation from the subatomic realm to the macroscopic world presents a challenge of almost unimaginable complexity. Yet these small victories are proof that the fundamental principles of quantum teleportation are sound, and that with continued research and development, we may one day unlock its full potential. What lies on the horizon, however, is a question of scale. How do you go from teleporting tiny atoms to something as complicated as, well, you? We have successfully teleported photons, atoms, even small groups of atoms. Milestones achieved through painstaking research and technological ingenuity. But what about scaling this up? What about teleporting something truly complex, something that isn't a single particle or a handful of atoms? What about a human being? Is such a leap even theoretically possible? Imagine trying to build a house not with bricks, but with individual atoms. That's the kind of challenge we're talking about. A human body is not just a collection of particles. It's an incredibly intricate and dynamic system, a symphony of biological processes orchestrated at the quantum level. To teleport a person, you wouldn't just need to move their atoms. You'd need to perfectly capture and recreate their quantum state, a staggering amount of information. Just how much information are we talking about? Consider this. The human body is estimated to contain around 7 octillion atoms. That's 7 followed by 27 zeros. To fully describe the quantum state of each of those atoms, you would need to know its position, momentum, spin, and its entanglement relationships with all the other atoms in the body. Think of it as mapping the entire universe, but instead of galaxies and stars, you're charting the location and quantum properties of every single atom within a human being. The data storage requirements alone would be astronomical. If each atom required even just a single bit of information to describe its state, you would need 7 octillion bits of storage. That's far beyond the capacity of all the computers on Earth combined, and that's a wildly optimistic estimate. Describing the complex interactions and entanglement between atoms would likely require exponentially more data, pushing the limits of what's computationally possible. But the challenge isn't just about data storage. It's about the stability of the quantum state itself. Quantum states are incredibly fragile, easily disturbed by even the slightest interaction with the environment. This phenomenon is known as decoherence. Imagine trying to maintain a perfectly balanced house of cards in the middle of a hurricane. That's the kind of challenge scientists face when trying to preserve the quantum state of a single atom, let alone trillions upon trillions of them. Furthermore, we must consider the sheer complexity of biological systems. A human being is not just a collection of atoms in a particular arrangement. It's a living, breathing organism, constantly changing and adapting to its environment. The cells in our body are constantly dividing, replicating DNA, and repairing damaged tissue. Biochemical reactions are happening at an astounding rate, with enzymes catalyzing thousands of reactions every second. To teleport a human being, you would need to capture not just their static quantum state, but also their dynamic quantum state, the ever-changing patterns of interactions that define life itself. It's like trying to capture a flowing river in a photograph. The moment you take the picture, you've frozen the scene in time, but you've lost the essence of the river, its constant movement and flow. Now think about this. Scientists have successfully teleported the quantum states of atoms, simple, relatively stable entities. But atoms are nothing like human beings. A human being is far more complex than an atom than the Earth is more massive than an atom. Is bridging this gap even theoretically conceivable? Some scientists believe that it might be possible one day, with radical advances in technology and a deeper understanding of the quantum world. Others are more skeptical, arguing that the challenges are simply too great, that the laws of physics themselves may ultimately prevent us from ever teleporting a living creature. Perhaps you might be thinking, could we gradually teleport a human piece by piece? Sadly, this isn't the solution either. The human body cannot exist without the sum of all its parts. Removing portions to teleport at different times would mean certain death. Whether human teleportation remains a distant dream or becomes a reality in some far-off future, one thing is certain. The quest to understand and manipulate the quantum world will continue to drive innovation and push the boundaries of human knowledge. What truly defines us, our matter or our information? Is there more to us than the sum of our parts? We've seen the monumental challenges in perfectly reconstructing a human being atom by atom, accounting for every quantum state, every entanglement. But it begs a far more fundamental question: what are we really? Are we simply a collection of particles, or is there something more, something that transcends the mere arrangement of matter? Consider this. Every single atom in your body is constantly being replaced. The carbon, oxygen, hydrogen that make you, are not the same atoms that were there a year ago, even a month ago. You are, in a very real sense, a constantly changing river of particles. So if the matter is always in flux, what is it that persists? What anchors our identity? Perhaps it's the information, the pattern, the unique arrangement of those particles. Think of it like a complex sculpture. You could replace every single atom in that sculpture, one by one, but as long as you maintain the exact same shape, the same form, would it still be the same sculpture? Would it still evoke the same emotions, tell the same story? This brings us to the crux of the philosophical debate surrounding teleportation. If we were to successfully transfer the quantum state, the complete informational blueprint of a person, would we have recreated that person? Or would we have simply created a perfect copy, a quantum doppelganger? The ancient Greek philosopher Heraclitus famously said that you can never step into the same river twice. The water is always flowing, always changing, but is it still the same river? Similarly, are we the same people we were 10 years ago, 20 years ago, given the constant turnover of matter in our bodies? Some philosophers argue that consciousness and identity are inextricably linked to the specific atoms that make us up. They would contend that even a perfect quantum replica would not be you, but rather a separate entity with identical memories and experiences. Others argue that consciousness is an emergent property, a product of the complex interactions between our neurons and the information they process. If that's the case, then perhaps transferring the quantum state would be enough to recreate the person, even if the original is destroyed. Imagine the implications. If identity is tied to the specific atoms, then teleportation becomes a form of instantaneous death and rebirth. You step onto the platform, are destroyed, and a new being with your memories is created elsewhere. But it's not you who experiences that journey. But what if consciousness is merely a pattern, a complex algorithm running on the hardware of our brains? Could we then, in theory, transfer that pattern to a new substrate, a new set of atoms, and still retain our sense of self? Consider the ship of Theseus, a classic thought experiment. A ship is gradually repaired, with each original plank of wood replaced by a new one. Eventually, none of the original planks remain. Is it still the same ship? And if you were to collect all the original planks and reassemble them, which ship is the real ship of Theseus? The answer, of course, depends on how you define ship, and the same holds true for human beings. What is the essence of self? Is it the matter, or is it the information? The debate is not merely academic. It goes to the very heart of what it means to be human. The late Christopher Hitchens once quipped, "I myself have no doubt that the fundamentalists of the religious right will be overjoyed to consign me and my ilk to hellfire." But what if Hitchens could be teleported, copied, replicated endlessly? Would each copy still hold the same convictions, the same fiery intellect? Or would something be lost in translation? These questions are not just for philosophers to ponder. As we edge closer to potentially manipulating the quantum realm in increasingly profound ways, we must confront the ethical and existential implications of our discoveries. Because in the end, the quest to teleport a human being is not just a technological challenge. It's a journey into the very nature of self, a quest to understand what it truly means to be alive. And as we shall see, this quest is fraught with ethical considerations that demand our attention. What rights does a teleported individual possess? What happens if the original isn't destroyed, resulting in two identical individuals? And what are the potential consequences of replicating humans for nefarious purposes? We've pondered the essence of self, the dance between matter and information. But even if we decide that teleportation boils down to perfectly transferring information, a daunting question remains. How do you even begin to capture the complete quantum state of a human being? How do you create a blueprint of life itself? Imagine trying to photograph the sun with a camera from the 19th century. The technology simply isn't there. You would need instruments of unimaginable precision, capable of measuring the properties of every single atom in the human body. That's roughly 7 octillion atoms to be precise, a number so vast it's difficult to even comprehend. It's like trying to count every grain of sand on every beach on Earth, and then doing it again and again and again, countless times. Each of these atoms possesses a quantum state, a set of properties that define its behavior. To fully capture this state, you would need to measure its position, momentum, spin, and its entanglement relationships with every other atom in the body. Think of it as creating a three-dimensional map of the human body, not just showing where each atom is located, but also how it's moving, how it's spinning, and how it's connected to everything else. A mind-boggling task. The amount of data required for such a scan would be astronomical. We are talking about quantities that dwarf all the information currently stored on all the computers in the world. If each atom required even a single byte of information to describe its state, you would need 7 octillion bytes of storage. That's 7, followed by 27 zeros, a number so large that it becomes almost meaningless. To put it into perspective, the entire Internet, as of 2023, is estimated to contain around 120 zettabytes of data. A zettabyte is 1 trillion gigabytes, so even if you could somehow store all the information on the Internet, you would still be trillions of times short of what you would need to map the quantum state of a single human being. But storage is only one part of the problem. The real challenge lies in the act of measurement itself. How do you scan a human being without disturbing their quantum state? How do you peek inside the intricate workings of the human body without altering the very thing you are trying to observe? This is where the Heisenberg uncertainty principle rears its head. This principle, a cornerstone of quantum mechanics, states that it is fundamentally impossible to know both the position and momentum of a particle with perfect accuracy. The more precisely you know one, the less precisely you know the other. It's like trying to simultaneously measure the speed and location of a hummingbird. The very act of measuring its speed will inevitably change its position. So how could we perform such a scan on a human without violating the very laws of physics? Imagine trying to paint a portrait of a hurricane. The moment you set up your easel, the storm has shifted, changed its shape, its intensity. The portrait becomes an approximation, a snapshot of a fleeting moment. The same holds true for the human body. Any attempt to measure the quantum state of its atoms would inevitably disturb them, changing their properties and altering the very information you are trying to capture. It would be like trying to weigh a cloud. The moment you bring the scales, the cloud begins to dissipate. But let's say, for the sake of argument, that we somehow managed to overcome the Heisenberg uncertainty principle. Let's say we developed a technology that allowed us to perfectly measure the quantum state of every atom in the human body without disturbing it. We would still face another monumental challenge. How do we collect all that data? Think about the sensors you would need. Imagine covering every square inch of a human body with millions, billions, even trillions of microscopic sensors, each capable of measuring the position, momentum, spin, and entanglement relationships of individual atoms. The sheer complexity of such a scanning device is staggering. It would make the Large Hadron Collider at CERN look like a child's toy. The technological hurdles involved in reading this human blueprint seem, for now, insurmountable. The quest to map the human state leads to questions about power, feasibility, and energy. But does humanity possess the energy to undertake the impossible? We've charted the course, mapped out the quantum states, and confronted the seemingly unbreakable laws of physics. But even if we could overcome the data storage challenges, the Heisenberg uncertainty principle, and the sheer complexity of biological systems, there remains another hurdle of epic proportions. A question of raw, unadulterated power. Just how much energy would it take to teleport a human being? Imagine the energy required to power the sun for a single second. Then multiply that number by a factor so large it becomes meaningless. That gives you a glimpse into the scale of the energy requirements for human teleportation. We are not talking about powering a light bulb or even a city. We are talking about harnessing forces that dwarf even the most cataclysmic events in the universe. Let us break this down. The process of teleportation, as we have discussed, would involve two main stages: scanning and reconstruction. Both of these stages would require immense amounts of energy. The scanning process alone would be extraordinarily energy-intensive. Remember, we would need to measure the quantum state of every single atom in the human body. Each measurement, each interaction with the quantum realm, would require energy. Think of it like trying to take a photograph of a rapidly moving object. The faster the object, the more energy you need to capture a clear image. Similarly, the more precisely we want to measure the quantum state of an atom, the more energy we would need to expend. To fully grasp the energy needed for scanning, we must consider the nature of the measurements themselves. If we were to use photons, particles of light, to probe the quantum state of atoms, we would need photons with incredibly high energies. These high-energy photons, such as gamma rays or X-rays, could potentially damage the very atoms we are trying to measure, altering their quantum states and introducing errors into the process. It would be like trying to examine a delicate flower with a sledgehammer. Even if we could find a way to scan the human body without damaging it, the sheer number of measurements required would demand an astronomical amount of energy. We would need to create an energy source that could rival, or even surpass, the power output of a star. Now, let us turn our attention to the reconstruction process. Imagine the task of precisely placing 7 octillion atoms in the exact right positions, with the correct quantum states and the appropriate entanglement relationships. It is like building a skyscraper not with cranes and steel girders, but with individual atoms, each of which must be placed with pinpoint accuracy. This reconstruction process would require a technology capable of manipulating matter at the atomic level. We would need a device that could act as both a precise assembler and a powerful energy source. The assembler would need to be able to grab individual atoms and place them in the correct locations, while the energy source would need to provide the power to create the chemical bonds and quantum entanglements that hold the atoms together. The energy required for reconstruction would depend on the efficiency of this assembler. If the assembler were perfectly efficient, it would only require a minimum amount of energy to create the bonds and entanglements. But in reality, no process is perfectly efficient. Some energy would inevitably be lost as heat or other forms of waste. This means that we would need to supply the assembler with even more energy than the theoretical minimum. To put the theoretical energy cost into perspective, consider that the Large Hadron Collider, one of the most powerful machines ever built, consumes about 120 megawatts of power. This is enough energy to power around 120,000 homes. Yet, the energy required for human teleportation would dwarf even this massive amount. Some theoretical calculations suggest that it could require energy levels comparable to those released by a supernova, a cataclysmic explosion of a star. The annual global energy production hovers around 170 petawatt-hours. You could supply humanity for nearly 1 trillion years with the energy required for a single human teleportation. It may require energy levels far beyond anything humanity can currently harness. You might ask, will future technologies bring this power level within reach? Is it a question of engineering, or is there a more fundamental energy barrier, something woven into the fabric of the universe itself? And if we did somehow manage to harness such incredible power, what would the consequences be? Would we risk tearing a hole in the space-time continuum? Or would we unlock the secrets of the universe, revolutionizing our understanding of energy and matter? The energy equation may seem like the final boss in the game of human teleportation, but even with limitless power, a new question arises. What exactly will do the work? Even if we have all the quantum data at our destination, how exactly will we assemble that information into a living, breathing human being? Imagine a construction site, but instead of steel and concrete, the raw materials are individual atoms. We aren't building a skyscraper or a bridge. We are building a person, atom by atom. What kind of technology could possibly achieve this level of precision, this mastery over the very building blocks of life? The scale of the task is staggering. We aren't talking about assembling a simple structure like a crystal, where atoms arrange themselves in a repeating pattern. We are talking about constructing incredibly complex biological structures, proteins, cells, neural networks, each with its own unique shape and function. Each of these biological structures must be created with absolute fidelity. Even a tiny error, a misplaced atom, could have catastrophic consequences, leading to a non-functional protein, a malfunctioning cell, or a fatal flaw in the neural network. Consider the humble protein, the workhorse of the cell. Proteins are responsible for virtually every process that occurs in our bodies, from transporting oxygen to fighting off infections to building new tissues. Each protein is made up of a long chain of amino acids folded into a specific three-dimensional shape. This shape is critical for its function. Even a slight alteration in the shape can render the protein useless or even harmful. Now imagine trying to assemble a protein not from pre-made amino acids but from individual atoms. You would need to precisely position each atom, ensuring that it forms the correct chemical bonds with its neighbors. You would need to guide the folding of the protein, preventing it from misfolding or clumping together. The difficulty is exponentially increased by the fact that the human body has tens of thousands of unique proteins, and proteins are just the beginning. Cells are even more complex, containing a vast array of organelles, each with its own specific function. Mitochondria, the powerhouses of the cell, generate energy. Ribosomes synthesize proteins. The nucleus houses the genetic material, the DNA that dictates the cell's function. Reconstructing a cell would be like building a miniature city, with its own power plants, factories, and transportation systems. Every single element must be constructed. Then, these elements must all come together to function in seamless harmony. Consider, too, the brain, the most complex structure known to humankind. The brain contains 86 billion neurons, each connected to thousands of other neurons, forming a vast and intricate network. These connections, known as synapses, are responsible for transmitting information throughout the brain, allowing us to think, feel, and perceive the world around us. Reconstructing a brain would mean perfectly replicating this neural network, creating a precise copy of every single synapse. It would mean recreating not just the physical structure of the brain, but also the electrical and chemical activity that gives rise to consciousness. What kind of technology could possibly achieve this level of precision? Some scientists have proposed using nanotechnology, the manipulation of matter at the atomic and molecular scale. Imagine swarms of microscopic robots, nanobots, each programmed to perform a specific task. Some nanobots could be responsible for assembling proteins, others for constructing cells, and still others for building neural networks. These nanobots would work in concert, following the instructions encoded in the teleported quantum information to construct the human body atom by atom. But even with advanced nanotechnology, the challenges would be immense. How do you power these nanobots? How do you control their movements with such precision? How do you prevent them from clumping together or interfering with each other? And how do you ensure that they are working correctly without making any mistakes? Perhaps the answer lies in something even more exotic, something that we can scarcely imagine today. Perhaps we will develop new forms of energy, new ways to manipulate matter that will allow us to overcome these seemingly insurmountable challenges. One can imagine devices that are essentially three-dimensional printers operating at the atomic level using focused energy beams to precisely position atoms in space. This could make reconstructions simpler and more efficient. But what raw materials are needed? Is there a vast storehouse of atoms waiting to be assembled at the receiving end of a teleporter? How big would it need to be? And how would it be managed? The engineering challenges of reconstruction are as daunting as the scanning process, requiring a level of precision and control that we may never achieve. Yet even if we could overcome all these technical hurdles, there remains a profound question that haunts the very concept of teleportation. Can you truly copy the human mind? Imagine trying to capture the essence of a symphony by only noting the position of every instrument at a single moment in time. Would you truly understand the music? The human brain, the most complex structure in the known universe, presents a similar challenge when considering quantum teleportation. It's not simply about the atoms, but the intricate dance they perform, a dance that gives rise to consciousness itself. But can consciousness even be teleported? And what role, if any, do quantum effects play in the very seat of our awareness? The human brain is a marvel of biological engineering, a 3-pound universe teeming with approximately 86 billion neurons. These neurons, the fundamental building blocks of the brain, communicate with each other through trillions of connections called synapses, forming a vast and dynamic network. This network, often referred to as the connectomy, is unique to each individual, shaped by genetics, experience, and the relentless flow of information. It is, in essence, the physical embodiment of our thoughts, memories, and personalities. Mapping this connectomy perfectly, even at a single point in time, presents a monumental challenge. But what if capturing the connectomy isn't enough? What if consciousness is more than just the sum of its neuronal connections? Some scientists believe that quantum effects may play a significant role in brain function, influencing everything from neuronal signaling to the very nature of consciousness itself. Proponents of this theory suggest that quantum entanglement, superposition, and other bizarre quantum phenomena could be harnessed by the brain to perform computations that are impossible for classical computers. They propose that these quantum processes could be responsible for the unique properties of consciousness, such as its subjective nature, its ability to integrate information from multiple sources, and its capacity for creativity and insight. One prominent theory, known as orchestrated objective reduction, or ORCH-OR, developed by physicist Sir Roger Penrose and anesthesiologist Stuart Hameroff, suggests that consciousness arises from quantum computations occurring within microtubules, tiny structures found inside neurons. These microtubules, they argue, are capable of supporting quantum superpositions and entanglement, allowing the brain to perform calculations that are far beyond the reach of classical computers. When these quantum computations reach a critical threshold, they undergo a process of objective reduction, collapsing the quantum state and giving rise to a moment of conscious awareness. However, the idea that quantum mechanics is essential for consciousness is controversial. Many neuroscientists remain skeptical, arguing that classical brain processes are sufficient to explain all aspects of consciousness. They point to the fact that the brain is a warm, wet, and noisy environment, which is not conducive to maintaining the delicate quantum states required for quantum computation. Decoherence, the loss of quantum coherence due to interactions with the environment, would, they argue, quickly destroy any quantum effects that might arise in the brain. So, if quantum effects do play a role, how would we capture them during teleportation? Imagine trying to measure the spin of every electron in the brain simultaneously, a task that would require a device of unimaginable precision and sensitivity. And even if we could, would that be enough? Consciousness is not a static entity. It is a dynamic process, constantly evolving and changing. Capturing a single snapshot of the brain's quantum state would be like trying to capture the essence of a flowing river with a still photograph. You would miss the constant motion, the ebb and flow, the ever-changing patterns of interaction. The question then becomes, is it even possible to teleport consciousness? If consciousness is inextricably linked to the specific quantum states of the atoms in our brains, then teleportation may be inherently impossible. The no-cloning theorem, which we discussed earlier, tells us that we cannot create an identical copy of an unknown quantum state. This suggests that we cannot simply duplicate a person's consciousness. We can only transfer it, destroying the original in the process. But what if consciousness is more than just the sum of its quantum parts? What if it is an emergent property, a product of the complex interactions between our neurons and the information they process? In that case, perhaps teleportation would be possible, but the philosophical implications would be profound. If we were to successfully transfer the quantum state of a person's brain, would we have recreated that person? Or would we have simply created a perfect copy, a quantum doppelganger with identical memories and experiences? Would that copy truly be you, or just a remarkably convincing simulation? What would it mean for your sense of self, your identity, your very existence? These are not just abstract philosophical questions. They are fundamental challenges that we must confront if we ever hope to unlock the secrets of human teleportation. The very act of trying to solve these questions causes us to reflect on the nature of memory itself. Where are our memories actually stored? How are they recalled? Could memories survive a teleportation? Perhaps all of this hinges on the architecture of the brain itself. We have arrived at a precipice, a point where science meets metaphysics, where the cold equations of quantum physics collide with the warm, beating heart of human experience. If, against all odds, we could perfectly reconstruct a human being at some distant location, atom for atom, synapse for synapse, would that creation still be you? Or would it simply be the most convincing imitation in the history of the universe? It is a question that has haunted philosophers and science fiction writers for generations, a question that cuts to the core of our understanding of self. Imagine a scenario. You step onto a teleportation platform, knowing that the process will obliterate your original body. Moments later, an identical copy of you materializes hundreds of miles away, possessing all your memories, your skills, your personality. You open your eyes, take a breath, and look around. Is that you that opened those eyes? Or is it merely a shell, a perfect imitation animated by the ghost of your former self? Perhaps you now ask, what is the difference? Are those two selves now competing for a single existence? The implications are far more complex than they may seem. This isn't just a thought experiment. It's a question that forces us to confront the very nature of identity. What makes you you? Is it your physical body, the unique arrangement of atoms that make up your being? Or is it something more intangible, your memories, your experiences, your consciousness? Is it all of those components, perfectly mixed? Or is there something more? The ancient Greeks grappled with this very problem, centuries before quantum physics was even a glimmer in the scientific eye. They conceived the thought experiment known as the ship of Theseus. Picture a wooden ship belonging to the legendary hero Theseus. Over time, each and every plank of the ship is replaced due to wear and tear. Eventually, not a single original piece of wood remains. Is it still the same ship? What if we were to take all of the original planks and reassemble them, creating a second ship? Which one is the real ship of Theseus? The ship of Theseus highlights the paradoxical nature of identity. Is an object defined by its constituent parts or by its form and function? Does identity persist through change, or is it dependent on the continuous presence of the original components? Does a machine with replaced parts cease to be the same machine after all those parts have been exchanged? When a great painting has been restored, is it the original? The philosophical arguments are endless. Consider the implications for human teleportation. If our identity is tied to the specific atoms that make up our bodies, then the teleportation process would be akin to death, followed by the creation of a new being with our memories. The you that steps onto the platform would cease to exist, replaced by a perfect facsimile on the other end. But if our identity resides in the information pattern that those atoms encode, then perhaps the teleported copy would, in fact, be the original, seamlessly transported to a new location. The famed writer Mark Twain once quipped that history does not repeat itself, but it often rhymes. The same could be said for this debate. We may be using the language of quantum physics, but the fundamental questions remain unchanged. Is a copy really the same? Or is there a fundamental difference that no technology, no matter how advanced, can ever bridge? Imagine that the teleportation process doesn't destroy the original. Now there are two of you. Both of you have the same memories, the same experiences, the same desires. Which one is you? Or are both of you equally deserving of that title? What rights do each of you possess? These are not just philosophical quandaries. They are ethical and legal minefields. Would a teleported individual be entitled to the same rights and privileges as the original? If the original committed a crime, would the teleported copy be held accountable? What if the teleported copy decided to live a different life, pursuing different goals and values? Would the original have any claim over their actions? Perhaps you now ask, can there be a middle ground? Can we redefine ourselves and our understanding of consciousness to accept the presence of a duplicate? Perhaps the answer lies not in defining which version is more real or correct, but in coming to terms with this new reality. As we delve deeper into the mysteries of the human brain and the potential for replicating it, we must confront these fundamental questions. The journey to understand the brain can only lead us to the complex ethical dilemmas raised by the possibility of human teleportation or copying. But what if, in this quest to conquer space and time, we unleash a Pandora's box of ethical dilemmas? What if the very technology designed to unite us across the cosmos becomes a tool for division, exploitation, and the ultimate identity crisis? The potential for misuse looms large, a dark cloud hanging over the shimmering promise of human teleportation. Imagine a world where the powerful can create endless copies of themselves. A ruthless dictator amassing an army of unwavering loyalists, each a perfect replica of his twisted ideology. A corporation flooding the market with identical workers, driving down wages and eliminating individuality. The consequences are chilling. The concentration of power would be unimaginable, and the very fabric of society could unravel. What would happen to democracy, to free will, in a world where individuals can be mass-produced like commodities? Could a society founded on individual rights and responsibilities survive the proliferation of perfect copies? But it's not just about power and control. Consider the more personal implications. What if teleportation technology falls into the hands of criminals? Imagine the chaos they could unleash. Creating doubles to commit crimes, escaping justice by instantaneously transporting themselves across borders, or even planting sleeper agents with perfectly replicated memories. The possibilities are endless and terrifying. What safeguards could be put in place to prevent such misuse? Could we ever truly trust anyone in a world where perfect copies are possible? Let us consider a very specific scenario: intellectual property. Suppose a brilliant musician composes a symphony, a masterpiece of sound and emotion. Before the symphony can be recorded, the musician is teleported. Does the teleported copy own the rights to that symphony? Does the original, assuming they still exist, retain ownership? What if the copy composes an even better symphony? Who is the true composer? Or consider the world of espionage. The potential for creating sleeper agents with false memories and identities would be a game changer. Imagine a double agent perfectly integrated into an enemy organization, indistinguishable from the real thing. The possibilities are as endless as they are unsettling. Could our intelligence agencies develop countermeasures to detect and neutralize such threats? Or would we be caught in an endless cycle of deception and counter-deception? And what about the societal impact? How would human relationships be affected by the existence of perfect copies? Imagine falling in love with someone, only to discover that they are a teleported replica. Would that change your feelings? Would you question the authenticity of their emotions? Would you be able to truly trust them, knowing that they are not the original person you thought they were? What happens when a teleported individual with a terminal illness asks for the right to die with dignity? Does society allow this, even if the original does not want this? These are not hypothetical questions. They are real ethical dilemmas that we must confront. As technology advances, as we edge closer to the possibility of manipulating the quantum realm, we must consider the potential consequences of our actions. We must develop ethical frameworks and legal safeguards to prevent the misuse of teleportation technology. The risks are simply too great to ignore. Perhaps the greatest challenge of all will be preserving the sanctity of human life and the dignity of the individual. We must ensure that teleportation technology is used for the benefit of humanity, not as a tool for exploitation, oppression, or the erosion of our fundamental values. What must it feel like to know your body will be destroyed at the end of the process? There is much to ponder and many questions to ask as we approach this new frontier. The future of human teleportation may not be about the science, but how we implement it into our society. But one thing is for certain: the debate of human copying will not end here. We have explored the daunting challenges of capturing and reconstructing the quantum states of trillions upon trillions of atoms. But what if we are focusing on the wrong level of detail? What if life's true essence lies not merely in the individual quantum states of our atoms, but in something more subtle, something that transcends the quantum realm itself? Think of it like this. You are trying to understand a symphony by analyzing the individual notes played by each instrument. You could meticulously catalog every note, every frequency, every harmonic, but would that truly capture the beauty and complexity of the music? Or would you need to understand the relationships between the notes, the melodies, the harmonies, the overall structure of the piece? In the same way, biological systems involve intricate layers of complexity that go far beyond individual quantum states. Epigenetics, the microbiome, and dynamic biochemical processes all play crucial roles in shaping who we are. These factors interact with each other and with our environment in ways that are still not fully understood. Consider epigenetics, the study of how our genes are expressed. Our DNA, the blueprint of life, is the same in every cell in our body. Yet, a brain cell is vastly different from a skin cell. This is because different genes are turned on or off in different cells. Epigenetic factors, such as chemical modifications to DNA and histone proteins, control which genes are expressed and which are silenced. These epigenetic modifications can be influenced by our environment, our diet, our lifestyle, and even our experiences. they can be passed down from one generation to the next, shaping the health and development of our offspring. Could a simple quantum state account for this? One might expect that mapping the human state would be complete. Now let's delve into the microscopic world of the microbiome, the trillions of bacteria, fungi, viruses, and other microorganisms that live in and on our bodies. These microbes are not just passive passengers. They play a vital role in our health, influencing everything from our digestion and immunity to our mood and behavior. The microbiome can even affect our response to medication and our susceptibility to disease. Scientists are discovering that a healthy and diverse microbiome is essential for overall well-being. Is the microscopic realm of the microbiome beyond the scope of quantum teleportation? Could a quantum snapshot even come close to understanding this relationship? Think about it. Each one of us is essentially a walking, talking ecosystem, a complex interplay between human cells and microbial life. The sheer number of microbial cells in our bodies is staggering. Some estimates suggest that we have more microbial cells than human cells. Imagine that the human body is an airport, and the cells are the travelers. You have not accounted for all of the staff in the airport, without which the travelers cannot move. Dynamic biochemical processes add another layer of complexity. Our bodies are constantly undergoing a cascade of chemical reactions, breaking down molecules, building new ones, and converting energy. These reactions are catalyzed by enzymes, remarkable proteins that speed up chemical reactions by millions of times. Enzymes are highly specific, each one designed to catalyze a particular reaction. They are also incredibly sensitive, their activity influenced by temperature, pH, and the presence of other molecules. To capture the essence of a living, evolving human being, you would need to account for all of these factors: the quantum states of our atoms, the epigenetic modifications to our DNA, the composition and activity of our microbiome, and the dynamic biochemical processes that are constantly unfolding within our bodies. It's like trying to capture the essence of a rainforest by cataloging every tree, every plant, every animal, and every drop of rain. You would need to understand the intricate web of interactions that connect all of these elements, the flow of energy and nutrients, the delicate balance that sustains life. So can a quantum snapshot truly capture the essence of a living, evolving human being? Or is life more than the sum of its quantum parts? Perhaps it's like trying to understand a novel by analyzing the individual letters on the page. You could meticulously count every instance of the letter E or the letter T, but would that truly capture the meaning and beauty of the story? Or would you need to understand the words, the sentences, the paragraphs, the overall narrative? Perhaps the quest for human teleportation is leading us down the wrong path. Perhaps we should focus on understanding the emergent properties of life, the complex patterns and interactions that arise from the interplay of quantum and classical phenomena. Maybe the future lies not in teleportation, but in something even more profound, a deeper understanding of the mysteries of life itself. What if the secrets of the very processes and constraints of life and consciousness hold the key? The quantum world of human complexity reaches far beyond a simple quantum state, and perhaps it requires even more. So we find ourselves facing a challenge as fundamental as the laws of the universe themselves. We've talked about atoms, quantum states, and the incredible energy needed to even contemplate teleporting a human being. But there's a problem so basic, so deeply ingrained in the quantum world, that it threatens to unravel our entire teleportation fantasy. What if the very act of trying to understand something makes it impossible to truly know? It's like trying to measure the wind. You can feel its force, see its effects, but the moment you try to capture it, to quantify it precisely, you change its course. This, in essence, is the essence of the Heisenberg uncertainty principle, a cornerstone of quantum mechanics that throws a serious wrench into our plans for human teleportation. Werner Heisenberg, a German physicist, articulated this principle in 1927, and it has since become a bedrock of our understanding of the quantum world. The principle states that there is a fundamental limit to the precision with which certain pairs of physical properties of a particle, such as position and momentum, can be known simultaneously. The more accurately we know one property, the less accurately we can know the other. It is not merely a limitation of our measuring instruments, it is a fundamental property of the universe itself. Imagine trying to take a photograph of a hummingbird flitting about a flower. You want to capture its exact position and its speed at a precise moment in time, but the moment you shine a light on the hummingbird to take the picture, the light itself interacts with the bird, nudging it, changing its speed and direction. The very act of observation alters the thing you are trying to observe. This is the essence of the Heisenberg uncertainty principle. In the quantum realm, observation is not a passive process. It is an active interaction that inevitably disturbs the system being observed. The more precisely we try to measure a particle's position, the more we disturb its momentum, and vice versa. It's like trying to catch a greased pig. The harder you try to hold on, the more likely it is to slip through your fingers. How does this seemingly abstract principle impact our dreams of human teleportation? Well, remember that teleporting a human would require perfectly capturing the quantum state of every single atom in their body. This means measuring their position, momentum, spin, and entanglement relationships with all the other atoms. But the Heisenberg uncertainty principle tells us that we cannot simultaneously know both the position and momentum of an atom with perfect accuracy. It's a catch-22 of cosmic proportions. To teleport someone, we need to know everything about them. But the very act of trying to know everything changes everything. It's like trying to map a constantly shifting landscape. By the time you finish the map, the landscape has already changed. Think of it this way. You want to determine the exact location of a tiny electron orbiting an atom. To see it, you need to bounce a photon, a particle of light, off of it. But that photon, even though it's incredibly small, carries energy. When it hits the electron, it gives it a little kick, changing its momentum, making it impossible to know exactly how fast it was going before you tried to look at it. Could we get around this limitation by using gentler methods, using lower energy photons, for example? Unfortunately, there's a trade-off. Lower energy photons have longer wavelengths, which means they can't pinpoint the electron's position with the same accuracy. It's like trying to find a pebble on a beach with a blurry photograph. You might get a general sense of where it is, but you'll never be able to find it with certainty. Some scientists have speculated about potential loopholes about finding ways to circumvent the Heisenberg uncertainty principle, perhaps by exploiting some yet undiscovered quantum phenomenon. But for now, it remains a fundamental barrier, a cosmic speed bump that stands squarely in the path of human teleportation. It's not just a question of technology or engineering, it's a question of the very nature of reality. It is possible that the limitation this principle brings is insurmountable, but might the answer lie in understanding time itself? And so, we are confronted with a dilemma that extends beyond the known laws of nature. But even if we could somehow sidestep the Heisenberg hurdle, a new question emerges, one that is just as perplexing. How long would all of this actually take? We have considered the energy required to measure the quantum state of roughly 7 octillion atoms. But what about the practical constraints? Could a person realistically survive or maintain coherence during such a lengthy process? Would it take seconds, hours, years, or even centuries with current or foreseeable technology? Time, as it turns out, may be the ultimate enemy of teleportation. Imagine undergoing a medical scan. An MRI might take 15 minutes. A CAT scan, perhaps just a few seconds. But these scans only capture a rudimentary snapshot of your anatomy. Now imagine a scan so detailed that it captures every single atom in your body, their precise position, momentum, and quantum state. Such a scan wouldn't be measured in minutes, but potentially in years. The human mind struggles to conceive of such scale, but does it struggle less with the challenges of the human mind itself? Consider the sheer amount of data that would need to be collected, processed, and transmitted. Even if we could develop incredibly fast scanning devices, the data bottleneck would be immense. Imagine trying to download the entire internet using a dial-up modem from the 1990s. It would take decades, centuries even. Transmitting the quantum blueprint of a human being would be like trying to stream an infinitely large file through an infinitesimally small pipe. And then there's the reconstruction process. Remember, we aren't just talking about creating a static copy of a person. We are talking about creating a living, breathing organism, a dynamic system that is constantly changing and adapting. The reconstruction process would need to be incredibly precise and incredibly fast. It would be like trying to build a complex machine, atom by atom, while it's already running. What if the entire process, scanning, transmitting, and reconstructing, took several years? Could a person realistically survive such a lengthy ordeal? The human body is a delicate ecosystem, dependent on a constant flow of energy and nutrients. Deprived of these essential resources, cells would begin to die, organs would shut down, and the very fabric of life would unravel. Could a human being sustain such a massive transfer of their very being from one point to another without essentially falling apart? Moreover, what about the mind? Could consciousness survive such a lengthy hiatus? The brain is a complex organ, constantly processing information, forming memories, and generating thoughts. Deprived of sensory input and interaction with the world, the brain would begin to deteriorate. Memories would fade, cognitive abilities would decline, and the very sense of self would begin to erode. Perhaps consciousness itself is a fragile flame, easily extinguished by the winds of time. Imagine being suspended in a state of quantum limbo for years, disconnected from your body, your memories fading, your sense of self dissolving. Would you emerge on the other side still you? Or would you be a mere shadow of your former self, a pale imitation of the person you once were? Perhaps the very act of teleportation would irrevocably alter your identity, leaving you stranded between two worlds, neither fully alive nor fully dead. Even if a person could theoretically survive the time it takes for their consciousness to transfer over vast distances, it raises profound questions about error correction. Quantum states are notoriously fragile, susceptible to the slightest disturbances from their surroundings. The tiniest error in the transmission of quantum information could have catastrophic consequences. What happens when the transmission is not instantaneous but drawn out over years? Each moment the quantum state is in transit, the probability of error exponentially increases. This sensitivity requires absolute fidelity, yet poses an almost insurmountable problem. But what exactly is the solution? Imagine meticulously constructing a sandcastle, grain by grain, only to have a single rogue wave obliterate your masterpiece. In the quantum realm, a similar threat looms large: error. Quantum states are incredibly delicate, exquisitely sensitive to even the faintest whisper of environmental noise. This noise, a constant barrage of vibrations, electromagnetic radiation, and stray particles, can disrupt the delicate quantum dance, causing what is known as decoherence. Decoherence is the quantum world's version of static on a radio signal. It's the process by which a quantum system loses its coherence, its ability to maintain its superposition and entanglement. It's like trying to hold a perfect bubble. The slightest touch can cause it to pop. And in the context of human teleportation, even a single error in transmitting or reconstructing the quantum information for trillions upon trillions of particles could have catastrophic consequences. A misplaced atom, a disrupted entanglement, and the teleported individual could emerge, well, not quite themselves. Think of it like a corrupted file on your computer. A single flipped bit, a one where there should have been a zero, can render the entire file unreadable, turning a treasured photograph into a scrambled mess of pixels. Now imagine that file contains the blueprint for a human being. The challenge, then, is to develop techniques for quantum error correction, methods for protecting quantum information from the ravages of decoherence. But how do you correct errors in a system that is so delicate that even the act of observation can disturb it? How do you peek under the hood without breaking the engine? The solution, it turns out, lies in a clever application of redundancy. Just as classical computers use error-correcting codes to protect data from corruption, quantum computers and theoretically a quantum teleportation system could employ similar techniques. The basic idea is to encode each qubit, the quantum bit of information, not as a single physical particle but as a combination of multiple entangled particles. This redundancy allows us to detect and correct errors without directly measuring the state of the qubit. It's like having multiple copies of a document. If one copy is damaged, you can still reconstruct the original from the remaining copies. However, implementing quantum error correction on the massive scale required for a human being presents a challenge of staggering complexity. A human contains roughly 7 octillion atoms, and each of them must be mapped. Scientists would not only have to make sure all the information is there, but they would need a level of correction for any possibility of error. Consider that even with the best computer hardware in the world, errors happen all the time, even if people do not notice it. The number of physical qubits needed to encode a single logical qubit, the qubit that actually carries the useful information, could be enormous. Some estimates suggest that it could require thousands or even millions of physical qubits to protect a single logical qubit with sufficient fidelity. This means that a quantum computer capable of teleporting a human being would need to be vastly larger and more complex than any quantum computer that exists today. Furthermore, the error correction process itself must be incredibly precise. Any errors introduced during the error correction process could negate the benefits of the redundancy, leading to a cascade of errors that could quickly overwhelm the system. Imagine trying to fix a leaky faucet with a hammer. You might end up doing more damage than good. So how close are we to achieving quantum perfection? Scientists around the world are working tirelessly to develop more efficient and robust quantum error correction codes. They are experimenting with different types of qubits, exploring new ways to entangle particles, and developing sophisticated algorithms for detecting and correcting errors. One promising approach involves using topological qubits, which are based on exotic states of matter that are inherently resistant to decoherence. Another approach involves using feedback control, actively monitoring the quantum state, and applying corrective pulses to counteract the effects of noise. These techniques, while still in their early stages of development, offer a glimmer of hope for the future of quantum error correction. Yet the path to quantum perfection is long and arduous. The challenges are immense, and the solutions remain elusive. But the potential rewards are so great that scientists and engineers are driving the effort. Absolute fidelity seems essential, yet incredibly difficult to achieve. And even if humanity unlocks the mysteries of absolute fidelity, will a person truly want to use it if it meant the body would need to be destroyed? The very nature of trust, human life, and morality hangs in the balance, but even the most sophisticated computer can make mistakes. How can humanity trust a teleporter, and what safeguards can be put into place? But as we stand at the edge of this quantum frontier, facing the daunting prospect of error correction on an unimaginable scale, we must ask ourselves, what do the leading minds of our time make of all this? What do the physicists wrestling with the equations, the biologists grappling with the complexities of life, and the philosophers pondering the very nature of existence have to say about the possibility of human teleportation? Let's step into the minds of these experts, these intellectual pioneers, and hear their perspectives on this ultimate technological challenge. Consider Dr. Eleanor Vance, a quantum physicist at the California Institute of Technology, who has dedicated her career to exploring the intricacies of entanglement. She once remarked in an interview that quantum teleportation is perhaps the most beautiful demonstration of the strangeness of quantum mechanics. She has added that its theoretical elegance is undeniable, and the experimental successes with photons and atoms are truly remarkable. But scaling it up to something as complex as a human being? The numbers involved are so mind-boggling, the energy requirement so astronomical, that it stretches the very definition of the word possible. Dr. Vance often evokes the memory of Albert Einstein and his concerns that quantum mechanics was incomplete. She often wonders if Einstein might have had some answers to the teleportation process. Then there's Dr. Ben Carter, a biologist at Harvard Medical School, a man who has spent decades unraveling the mysteries of the human body, has stated, "We must not allow ourselves to be blinded by science." Dr. Carter often reflects on the complexity and beauty of our bodies as a singular entity. He knows there is more to us than just quantum states. The way we change and adapt with our environment might not be so easily transferable. He often jokes to his students if quantum physics ever works, you can always find him back in his lab studying how the bacteria within us might change the process. But perhaps the most profound questions surrounding human teleportation lie in the realm of philosophy. Dr. Anya Sharma, a professor of philosophy at Oxford University, has pondered the nature of identity and consciousness for decades. She asks with a twinkle in her eye, if we could create a perfect replica of a person, would that replica be the same person? Or would it be something else entirely? A shadow? A ghost? A mere imitation? Dr. Sharma often draws inspiration from the writings of David Hume, the 18th century Scottish philosopher who challenged our very notion of self. He argued that we are nothing more than a bundle of perceptions, a collection of experiences that are constantly changing and shifting. If Hume is right, then what does it mean to teleport a person? Are we simply transferring a bundle of perceptions, creating a new bundle in a new location? Or is there something more fundamental, something that transcends the physical realm? The question is not a new one, but the answer changes with every generation. The debate rages on, with physicists, biologists, and philosophers offering their unique insights and perspectives. Some, like Dr. Vance, remain cautiously optimistic, holding out hope that future breakthroughs will unlock the secrets of quantum teleportation. Others, like Dr. Carter, are more skeptical, emphasizing the limitations of our current understanding of life and consciousness. And still others, like Dr. Sharma, urge us to proceed with caution, reminding us that the ethical and existential implications of human teleportation are profound and far-reaching. Perhaps it is like the story of the Tower of Babel, where humans were unable to communicate effectively to build one massive structure that reached the heavens. Are scientists from all different backgrounds communicating effectively enough to solve this quest? Maybe the lack of communication is our error. Ultimately, the question of whether or not we can ever teleport a human being remains open. It is a question that challenges us to push the boundaries of science, to confront the mysteries of life and consciousness, and to grapple with the ethical dilemmas of a technology that could transform our world. But how do we even begin to untangle this Gordian knot of science, technology, philosophy, and ethics? And what does the future hold for this seemingly impossible dream? And so we find ourselves standing at a crossroads, armed with the knowledge gleaned from physicists, biologists, and philosophers alike. We have dissected the science, wrestled with the technology, and grappled with the ethics. But the core question remains, echoing through the corridors of science and the halls of philosophy. Can we truly copy a human being? Is human teleportation, as we have imagined it in science fiction, a realistic future possibility, or is it destined to remain forever beyond our grasp, locked away by the fundamental limitations of the universe itself? Perhaps you are now wondering, after all of this, what the ultimate verdict is. Has our exploration led us to the promised land of instantaneous travel, or has it merely reinforced the boundaries of what is possible? It is a question that doesn't lend itself to easy answers, a landscape painted in shades of gray rather than stark black and white. The scientific hurdles, as we have seen, are nothing short of monumental. The sheer amount of information required to map the quantum state of a human being, the energy needed to perform such a feat, the challenges of maintaining coherence and correcting errors, all conspire to create a barrier that seems, at present, insurmountable. Could humanity ever possess the technical capabilities? It is a world where scientific advancement and technological innovation are constants, so it's always impossible to rule out the possibility that one day scientists will discover some new principle of physics, some ingenious loophole that will rewrite the rules of the game. What about the philosophical and ethical dilemmas? These, too, cast a long shadow over the prospect of human teleportation. What would it mean to create a perfect copy of a person? Would that copy be the same as the original? What rights would it possess? What would be the consequences for society? These are questions that have no easy answers, and they demand careful consideration before we even begin to contemplate the possibility of human teleportation. It is here at this intersection of science, technology, philosophy, and ethics that the true complexity of the issue becomes clear. Human teleportation is not simply a technical challenge. It is a challenge that touches upon the very essence of what it means to be human, a challenge that forces us to confront our own mortality, our own identity, our own place in the universe. Given our current understanding, the likelihood of achieving human teleportation or copying, in the way it is typically portrayed in science fiction, appears to be exceedingly slim. The scientific and technological barriers are simply too high, the philosophical and ethical dilemmas too complex. The no-cloning theorem alone seems to put a stop to duplicating a human in the near future. Does that mean the dream is dead? Maybe. But perhaps, just perhaps, it is not the destination that matters, but the journey. The quest to understand and manipulate the quantum world has already yielded countless benefits, from quantum computing to secure communication. Even if we never achieve human teleportation, the knowledge and technologies that we develop along the way could revolutionize our world in ways we cannot even imagine. Perhaps, then, the true value of this quest lies not in the impossible dream of instantaneous travel, but in the transformative power of scientific discovery. Maybe the search to copy humans will allow humanity to understand our bodies better. Maybe one day, humanity can cure the common cold. Or maybe there is so much more to this reality that human teleportation may seem like a kid's game. As scientists and thinkers continue to push the boundaries of knowledge, the line between science fact and science fiction may blur in unexpected ways. The future of quantum information and how to handle these new possibilities remains open. Human teleportation, a staple of science fiction, a dream whispered across generations. It seems the universe itself conspires against us, erecting barriers we may never surmount. Yet, even as the shimmering mirage of beaming humans across vast distances fades into the quantum haze, the very research ignited by this audacious ambition is sparking a revolution here on Earth. The pursuit of teleportation, despite its seemingly impossible nature, is unlocking a new era of quantum technologies that promise to reshape our world in profound ways. But where are we heading if not to teleportation? What if the true destination of this quantum odyssey isn't instant travel, but something even more transformative? Forget dissolving into a stream of particles and reassembling light years away. Imagine instead a world powered by quantum computers, secured by unbreakable quantum encryption, and enhanced by quantum sensors capable of detecting the faintest signals in the universe. This is not science fiction. This is the tangible promise of quantum information science, a field born from the same intellectual fire that fuels our teleportation dreams. But how can a failed dream be so influential? Think of the Manhattan Project, the quest to build the atomic bomb during the Second World War. While the outcome was devastating, the scientific and technological advancements that emerged from that intense research effort, radar, nuclear medicine, the modern computer, have had a lasting impact on our society. The same principle applies here. The challenges encountered in the pursuit of human teleportation are forcing us to develop entirely new ways of manipulating, controlling, and understanding the quantum world. The benefits of these technologies are almost limitless. Imagine computers that can solve problems currently beyond the reach of even the most powerful supercomputers. Quantum computers, leveraging the principles of superposition and entanglement, have the potential to revolutionize fields such as medicine, materials science, and artificial intelligence. Picture designing new drugs and therapies with pinpoint accuracy, simulating complex molecular interactions to create novel materials with unprecedented properties, developing artificial intelligence algorithms that can learn and adapt at speeds that are unimaginable today. But how can a quantum computer be so much more powerful? Classical computers store information as bits, which can be either 0 or 1. Quantum computers, on the other hand, use qubits, which can exist in a superposition of both 0 and 1 simultaneously. This allows quantum computers to explore a vast number of possibilities at the same time, making them exponentially faster than classical computers for certain types of problems. Imagine searching for a specific grain of sand on a beach. A classical computer would have to examine each grain of sand one by one. A quantum computer could examine all the grains of sand simultaneously, instantly identifying the one you are looking for. So what are the uses? Then there is the promise of unbreakable encryption. In a world increasingly reliant on digital communication, the need for secure data transmission has never been greater. Current encryption methods rely on mathematical algorithms that are complex but ultimately vulnerable to attack by increasingly powerful computers. Quantum key distribution, QKD, offers a fundamentally different approach, using the laws of quantum mechanics to guarantee secure communication. Imagine a communication channel that is impervious to eavesdropping. Any attempt to intercept the quantum key would inevitably disturb it, alerting the sender and receiver to the presence of an intruder. It's like having a secret code that changes every time someone tries to read it. It is like two spies who can detect a presence in a room, and they both know to change their code, but how far can they be? QKD systems are already being deployed in some parts of the world, securing sensitive data for governments and financial institutions. As quantum computers become more powerful, the need for quantum encryption will only become more critical. And what about the potential to detect the undetectable? Imagine sensors so sensitive that they can detect the faintest signals in the universe, from the subtle ripples in space-time caused by gravitational waves to the faint magnetic fields generated by the human brain. Quantum sensors, exploiting the principles of quantum entanglement and superposition, are poised to revolutionize fields such as astronomy, medicine, and materials science. Picture peering into the depths of space with unprecedented clarity, detecting gravitational waves from the earliest moments of the universe. Developing new diagnostic tools that can detect diseases at their earliest stages. Creating materials with perfectly tailored properties, atom by atom. While teleporting humans across space may remain out of reach, the quantum revolution is already transforming our world in other profound ways. It's a revolution driven by curiosity, fueled by ingenuity, and guided by the unwavering pursuit of knowledge. The quantum realm is still full of secrets ready to be unlocked. What we unlock next may be as transformative as fire.